Hello students and welcome to this fourth lecture of the mechanical properties of the fluids. So till now we have discussed the number of terms, number of concepts of the fluid, its properties, the ideal fluids and its property, and we have seen the 3 to 4 derivations also. Now we will revise the derivation that we have derived in the last previous video. So students, this is the last expression diagram that we have to derive the equation form. So first of all we have to consider the tank filled with the water. So this is the tank filled with the water, and we have to assume the imaginary cylinder of the horizontal base area A, and the height will be h, which will be derived from the x1 minus x2. Now the x1 and x2 are the heights measured from the reference point. X1 and x2 are the heights measured from the reference point, and the height increasing upward. Now in this case the x1 should be greater than x2. Now the vertical forces acting on the cylinder. Now as the imaginary cylinder, we have imagined to find out the forces, find out the pressure due to the imaginary cylinder. Now the three types of forces will be acting over that cylinder. How and where this will be acting, we will see now. So students, these forces are as listed on your screen. The first one is the force F1 bar acts downward at the top surface of the cylinder, and due to the weight of the water column above the cylinder. Means students, as you can see the F1 bar in the diagram, it is lying over the upper surface, it is over the top surface of the cylinder, and which has been created by the water which has been over the surface of that top of the imaginary cylinder. So this is the F1 bar, and the second one force is F2 bar, which is acts downward at the bottom surface of the cylinder, and it is due to the water below the cylinder. Now this is the F2 bar. The second type of force is F2 bar, which you can see in the diagram, and which has been created by the water which is lying below the bottom surface of that imaginary cylinder. So these are the two forces, F1 bar and the F2 bar. Now the third one force is the gravitation force on the water enclosed in the cylinder, and which may be given as the product of mass and the gravity, means the m into g. Now m is the mass of the water inside the cylinder, means m is nothing but the mass of the water which is enclosed inside the cylinder. Now water is an static equilibrium, means the forces will be balanced in this static kind of equilibrium, and the forces on the cylinder are balanced. Thus the balance of these forces will be the magnitude of this force can be written, we will see now. So first of all we have to understand the three types of forces, F1 bar, F2 bar. F1 bar is at the top of that imaginary cylinder, which will be occurred with because of that water which is lying over the top side of that imaginary cylinder. And the F2 force is the force which is at the bottom surface of that imaginary cylinder, which has been created by the force by that liquid which is lying below the base of the imaginary cylinder. And the third one is the gravitation force, which has been given by that mg, which will be acting over that cylinder inside that container or inside that vessel. Now student, this balance of these forces, their magnitude will be given as you can see, the F2 is equal to F1 plus mg, and while P1 and the P2 are the pressures at the top and the bottom surface of the cylinder respectively. Means P1 and P2 are the two pressures which we have considered, which will be acting over the top and the bottom surface of the cylinder respectively due to the fluid. Now this value means F1 will be P1 into A, means this we have derived from the formula pressure is equal to force upon area, from which we have made some arrangement. Then we will find out the value of F1, which will be P1 into A. Similarly we have find the value of F2, then these value we are going to put into that original equation. But before that we have calculated the value of M also, which is mass is nothing but the density into volume, which will be rho into V, and further m will be rho into A into h, which may be written as x1 minus x2. So the total value of m will be rho into A into x1 minus x2. So these three values we will put into the equation. Then we can obtain the original equation as. Now students, while we putting this value into this equation, then the equation will become the P2 into A will be instead of F1, the P1 into A will be instead of that F1, and plus rho into A into G into bracket x1 minus x2 will be instead of M. So the total equation will be P2 into A is equal to P1 into A plus rho A G into bracket x1 minus x2. So the A value, the A term which is on the either side of the equality sign, so it will be get cancelled automatically. Then the P2 will be is equal to P1 plus rho G into bracket x1 minus x2. So this is the final expression that we have derived, which we can use to find the pressure inside a liquid and also the atmospheric pressure. So this is the derivation and the expression that we have derived in the previous video. If you want to learn in detail, then you can visit the previous video and you will get it very easily. So students, this is the entire part that we have learned. Now we will see the next part of this chapter. Now students, to find out the pressure P at depth h below the liquid surface, we have to consider let the top of the imaginary cylinder be at the surface of the liquid. Means as you can see in the diagram, student, so the top of that top side or the top surface of that imaginary cylinder will be as equal to the water level of that water which is inside the container. So as you can see. Now after that, let the level be x1, means let the x2 be the some point at depth h, as you can see in the diagram, where is the x1 which is lying over the surface of that water and x2 is at some depth h from that surface of the water from the top surface of that imaginary cylinder. Now let P0 be the atmospheric pressure at the surface, means at the surface of that liquid, or you can say at the top surface of that imaginary cylinder is the P0 is the atmospheric pressure, means at the x1. Then the x1 will be 0 and the P1 will be equal to P0. So we can say that the x2 is equal to minus h and the P2 will be P. So the students, x1 is equal to 0, P1 will be equal to P0, that is the initial pressure, and the x2 will be, which is at some depth from the surface of the water, it will be minus h. So as it is in depth, now the P2 will be equal to P. Now the above equation which we had derived, when we put this value, when we put this all values in above equation, then equation will become P is equal to P0 plus rho Hg. So this will be the derived equation. So this equation gives us the total pressure or the absolute pressure P at depth h below the surface of the liquid. The total pressure P at the depth h is the sum of first one P0, the pressure due to the atmosphere which acts on the surface of the liquid, and the H rho G, the pressure due to the liquid at a depth. So this is nothing but the summation, and which will be gives us the absolute pressure P, which will be P0 plus rho Hg. So this is the derivation that we have obtained, that we have derived after the doing the consideration at the consideration as the top surface of that imaginary cylinder is equal to the water level or the water surface. Now in general we can say that the difference between the absolute pressure and the atmospheric pressure is called as a gauge pressure. So by rearranging the above equation, the above expression, we can state the above equation as the difference between the absolute pressure and the atmospheric pressure is called as a gauge pressure. Now the gauge pressure at depth h below the liquid surface now given as the P minus P0 is equal to rho Hg. So this is the gauge pressure that we have obtained by making some rearrangement into the derived above equation. Now students, the equation that we have derived, P minus P0 is equal to rho hg, which is the termed as the expression for the gauge pressure. This is also applicable to the levels above the liquid surface. Now it gives the pressure at the given height above the liquid surface. Now in terms of atmospheric pressure P0, by the assuming the atmospheric density is uniform up to that height. Now we'll be looking further toward the atmospheric pressure at the distance d above the liquid surface. So first of all, we have seen at some height below the surface of that liquid. Then we have saw as the top surface of that cylinder is equal to at the water level, and we will be seeing now the atmospheric pressure is at the distance d above the liquid surface. So this is the third derivation that we are going to see now. Now as you can see the diagram, students, that itself expressed that the x1 will be equal to d. Now x1 will be equal to d and the p1 will be equal to p, as you can see from the diagram. Now the x2, which is the bottom level of that imaginary surface, is equal to 0, and the p2 means the pressure at the bottom level of that imaginary surface or at the surface of the water is the p0, and the rho will be the rho air, means density of that water is equal to density of that air. So from this whole considerations we can derive the equation by putting this all values into above equation. We can obtain that the P is equal to P0 minus d rho air into G, means the pressure above the imaginary cylinder at the top side will be equal to the subtraction of pressure at the bottom side of the imaginary cylinder or at the surface level of that liquid minus the product of that depth over which the liquid level is situated, means from the reference point, into the density of air into that gravity or the acceleration due to gravity. So this is the expression that we have obtained, that the change of atmospheric with the height. So these are the three types of expression that we have derived. So which are those? We will just conclude them in short in order to get you simultaneously three of these equations. So this is the first case from which we have derived the equation, that the imaginary cylinder was lying inside the water at some height. At some height means at some height from the bottom of that container. The forces we have already discussed. So the equation that we have derived from it is the P2 is equal to P1 plus rho into G into bracket x1 minus x2. So this is the equation that we have derived in this case. And this is the second case that we have seen, that the imaginary cylinder is at some depth, means is at some height below the surface of the water, is at some height h, you can see there, and the x1 and the x2 are the point at the top and at the bottom surface of that imaginary cylinder. So in this case the equation that we have derived is by putting the value x1 is equal to 0, means at the water surface x1 is equal to 0, and the P1, as you can see, it is the P0, means the initial one pressure, and the x2, the value x2 will be minus s as it is below the surface of the water, and the P2 will be the P. So in this case that we have derived this equation, P is equal to P0 plus rho hg. Now the third case we have seen that the bottom of the imaginary cylinder is lying over the surface of the liquid. In this case we have derived the equation as by putting the value x1 is equal to d, means as the distance between x1 and the x2 is d, and the p1 is equal to p and x2 is equal to 0, P2 is equal to P0, and the density of the air is equal to density of that water. In this case, we have derived the P is equal to P0 minus D into rho of the density of air into G. So this much we have seen. The next part we will see in the next video. Thank you so much.